Good morning to all. Is it screen is visible to all?
Yes, sir.
Yes, sir.
So in the last lecture, we seen that one theorem. A field K is normal extension of a field F with characteristic 0 if and only if K is a splitting field of some polynomial over F. Okay. So today we will see one more theorem is there. Okay, wait a minute. Okay, the next theorem is let K be a normal extension of a field F. Let capital K be a normal extension, okay, normal extension of a field F, of a field capital F of the characteristic 0, okay, of the characteristic 0, okay, and let capital T be a subfield of K, be a subfield of the field K, okay, containing capital F. Then prove that T is a normal extension of F, normal extension of capital F if and only if sigma of T, okay, contained in T, for all sigma belongs to GKF. Okay, so this is the statement of the theorem. Let K be a normal extension of a field F of the characteristic 0 and T be a subfield of K containing capital F. Then we have to prove that T is normal extension of F if and only if sigma of T is contained in T. Okay, for all sigma belongs to GKF. What is the meaning of this one? Suppose this is F, the field F. This one is the field T containing F, and this one is the field K. Okay, so here the K is the normal extension of the field F with characteristic 0, and T is the subfield of K containing F. So we have to prove that this one, if T is the normal extension of F, then sigma of T contained in T. If you apply sigma on every element of T, okay, if you apply sigma on every element of these elements, okay, then sigma of T it must be contained in T for all sigma belongs to G. Okay. If the sigma of T is contained in T, then we have to prove that T is the normal extension of F. That is, if T is normal extension of F, what is the definition of normal extension? Fix the field of GTF is F.
Is F.
T is the normal extension of F. Okay. Now, proof. Look at the proof. Wait a minute. Since K is the normal extension of F, what is given to us? Since capital K is normal extension of capital F, and this implies K is what? Finite extension of F. Finite extension of F. Okay, so let write down all the given things first one. Let T be a subfield of K. T be a subfield of K containing F, containing capital F. Okay, so then if K is the finite extension of F and T is a subfield of K containing F, then T is also, capital T is also finite extension of F. Okay, T is also finite extension of capital F. Okay, here the K is finite extension of F. That means degree of K over F is finite. But T is the subfield of K. So hence degree of T over F is also finite. Hence T is also finite extension of the field F, which is hmm, which is characteristic 0. What is the characteristic of F? 0. Okay, now T is the finite extension of F with characteristic of F is 0. So this implies we have one theorem, T is simple extension of F. Okay, any doubt up to here?
No, sir.
Simple extension of F. That means there exists an element belongs to T, A belongs to T such that T is equal to F of A. This is the meaning of simple extension. Okay, so there is an element. There is an element. There is an element A belongs to T na or F?
F.
F. Is it correct?
No, sir. T.
A belongs to T such that T is equal to F of A. Okay, now we have to prove part 1. Okay, if part. If part. Suppose first assume sigma of T is contained in T. Sigma of T is contained in T. Okay, if you apply sigma on sigma of T म्हणजे काय T च्या प्रत्येक एलिमेंट वर जर सिग्मा अप्लाय केला तर तो T मध्येच कंटेन होतो. Okay, so here suppose sigma of T is contained in T for all sigma belongs to GKF. Okay, and we have to prove that T is normal extension of T is normal extension of capital F. Okay, any doubt up to here?
No, sir.
Okay, now we have K is the finite extension of F. That means degree of K over F is what? Finite. Okay, now suppose the degree of K over F is equal to N. What is the reason? K is finite extension of F. Okay, now since K is normal extension of field F, this is given to us. Look at here. K is normal extension of F. Okay, since K is normal extension of capital of a field F. Okay, capital F of characteristic 0. Okay, so this implies what it implies? The order of GKF. Okay, by corollary, we have order of GKF is equal to degree of K over F. That is GKF. This group is of finite. Okay, is a finite group. What is the reason? In the previous theorem, in the previous lecture, we have one corollary is there. Order of G K F is equal to degree of K over F. Okay, it is a corollary. Previous corollary. Okay, any doubt up to here?
No, sir. No, sir.
Yeah. So there are n elements are there in the group GKF. Okay, so let the elements sigma 1, sigma 2, up to so on sigma n be all distinct element, all distinct element of GKF. Okay, and assuming sigma 1 is the identity automorphism. Identity of GKF. Okay, is it correct? Okay, so sigma 1 is the identity of GKF. Since GKF is a group, okay, so identity must be present in GKF. Okay, give it reason. Since GKF forms group, okay, forms a group, it must contains identity. Okay, any doubt up to here?
No, sir.
Now, look at here. We have to show that sigma of t is contained in t. Okay, wait. We have sigma of t is contained in t, and we have to prove that t is the normal extension of f. Okay, so since if a is the any element belongs to t, okay, and what we have sigma of t belongs to contained in t. Sigma of t is contained in t. For all sigma belongs to, wait a minute, all sigma belongs to G, K, F. Okay, so this implies for all sigma belongs to G, K, F, we have sigma of t is contained in t. Okay, that means if you apply sigma on any element of t, then it must be contained in t. So that means sigma 1 of a, sigma 2 of a, up to so on sigma n. Okay, n elements are there in GKF. Sigma n of a belongs to t. Okay, any doubt?
No, sir.
Okay. Now the next point. Consider the polynomial one. Which one? Consider the polynomial. P of x is equal to x minus sigma 1 of a into x minus sigma 2 of a up to so on x minus sigma n of a. Okay, over the t. Okay, all the elements is from t. Sigma 1 of a belongs to t, sigma 2 of a belongs to t. Okay, so this p of x be the polynomial over t. Give it as an equation number 1. Okay, so this implies p of x is equal to, if you do multiply, we get x raised to n minus, again same method, sigma alpha 1 of alpha 1 into x raised to n minus 1 plus alpha 2 into x raised to n minus 2 up to so on plus minus 1 raised to n alpha n. Okay, where alpha 1, alpha 2 up to so on alpha n are what?
Belongs to F.
Elementary symmetric function. Okay, elementary symmetric functions. Elementary symmetric functions of the element of the elements sigma 1 of a, sigma 2 of a up to so on sigma n of a of t. Okay, any doubt?
No, sir.
Okay, now it can be easily seen that this alpha 1, alpha 2 up to so on alpha n are invariant under every sigma belongs to GKF. Okay, if we apply the sigma on this alpha 1, we get the element of again t. Okay, so here this alpha 1, alpha 2, look at here. Wait a minute. In the previous theorem, we proved this one, alpha 1, alpha 2, up to so on alpha n. These all are invariant under T. Okay, wait a minute. Okay, so here alpha 1, alpha 2. It can be easily seen that, write down, it can be easily seen that this alpha 1, alpha 2, up to so on, alpha n are invariant. Invariant with respect to this sigma belongs to GKF. Okay, GKF. Okay, what is the meaning of this one? That is sigma of alpha I is equal to alpha I for all sigma belongs to GKF. Okay, is it correct? Any doubt up to here?
No, sir.
The proof
Yes,
of
sir.
this statement. Okay, which one? This all these alpha 1, alpha 2 are invariant. Okay, it is given in the previous theorems. Okay, कालचा सोडून परवाच्या theorem मध्ये तो होता पहा. All these alpha 1, alpha 2 up to so on alpha n are invariant with respect to sigma. Okay, invariant with respect to sigma means sigma, if we apply sigma on that element, we get itself that element. Sigma of alpha I is equal to alpha I for all sigma belongs to GKF. Okay, now since capital K is normal extension of F, normal extension of F. Therefore, we have the fixed field of GKF is,
F.
wait a minute, fixed field of GKF is F. Okay, thus each alpha I belongs to F. Okay, and so this P of X be the element of F of X. Okay, any doubt up to here?
No, sir.
Okay, so this alpha 1, alpha 2 up to so on alpha n, these all the elements of F. Since K is the normal extension of F, that means fixed field of GKF is F. That means त्यातलं ते sigma घेतला आपण. If you take the sigma from GKF and apply on alpha 1, alpha 2, alpha 3, that elements belongs to what? F. कशामुळे आला हा alpha I belongs to F? Because the fixed field of GKF is F. Okay, what is the definition of fixed field of GKF? Take the collection of those elements of K which leaves every element of, okay, what is the fixed? कालच सांगितलं पुन्हा fixed field of GKF. काय meaning? Take A belongs to K such that sigma of A is equal to A for all sigma belongs to
GKF.
GKF. Okay, so by the definition of fixed field of GKF, this alpha I belongs to, कशात जाणार हा माझा alpha I? हा A जर माझा कशात गेलाय? Fixed field of GKF. So here the alpha I belongs to F. Okay, so this hence by the definition of fixed field of GKF, we get this alpha I belongs to capital F. Okay, any doubt now?
No, sir.
Okay, मार्क्स नीट लक्षात ठेवा. जर मार्क्स येत असेल तरच पुढचं कळत जाईल तुम्हाला. Okay, so here alpha I belongs to F, and so this polynomial P of X now belongs to capital F of X. Okay, so from equation 1, what is equation 1? This is the equation 1. We see that T splits the polynomial p of x belongs to f of x into the product of linear factors. Okay, this is the polynomial over t, and this p of x belongs to capital F of x. Okay, so any polynomial belongs to this polynomial p of x belongs to capital F of x, splits over t. Okay, hence from equation 1 we see that t splits the the polynomial p of x belongs to capital F of x into a product of linear factors. Okay, and also we have sigma 1 of a is equal to what? Sigma 1 is the identity automorphism. So sigma 1 of a is equal to a. Why? Because sigma 1 is identity automorphism. Okay, so is sigma 1 of a is equal to a is the root of p of x in t is equal to f of a. Okay, t is equal to f of a का आला है because since a generates t over f, okay, and no subfield of t which contains f, okay, hence t is equal to f of a. Okay, so t is the simple extension of f. Okay, look at here. T is the simple extension of f. So there is an element a belongs to t such that t is equal to f of a. Okay. So here sigma 1 of a is equal to a. Why? Because sigma 1 is an identity operator. Identity automorphism. So this is a is a root of p of x in t, which is equal to f of a. Since, what is the reason? Since this a generates t over capital F. Okay, so therefore a can be a can be in no proper subfield, subfield of capital T which contains F, capital F. Okay, so thus T is splitting field of P of x belongs to capital F of x. Okay, हा स्टेटमेंट लिहायची गरज काय? A can be in no proper subfield of T which contains F. That means T is the smallest field which contains both F and A. Okay, and over T, this polynomial P of x splits into linear factor. Okay, splitting field. What is the definition of splitting field? The smallest field. Okay, the smallest extension of that base field which splits that polynomial. Okay, into the linear factors. Okay, so why we are writing to this one? A can be no proper subfield of T which contains both F. So that is T is the smallest subfield which contains both F and A. Okay, so in between T and F, there is no proper subfield which splits this P of x. Okay, so here we get T is the splitting field of P of x. Okay, any doubt up to here?
No, sir.
Now, by the previous theorem, if K is the splitting field of F, look at here. What is the yesterday statement? If K is the normal extension of the field F of characteristic 0, if and only if K is the splitting field of some polynomial over F. Here we get K is the T is the splitting field of some polynomial, that is P of X of F. Then what? T is
T is normal extension of
extension
F.
field F. Okay, so here we get by previous theorem, yesterday's theorem, we get here if this the T is the splitting field of P of X belongs to capital F of X, thus capital T is a normal extension. Normal extension of capital F. Okay, what is the previous theorem? Previous theorem. एक्झाम मध्ये तुम्हाला लिहावं लागेल प्रिव्हियस थेरम काय तो. What is that statement? If K is normal extension of F with characteristic 0. क्या होता statement? Then what is that statement? Wait a minute. If K is the normal extension of the field F with characteristic 0, if and only if K is a splitting field of some polynomial over F. Okay. So by this theorem, here we get that T is the splitting field of P of X belongs to capital of X. So hence T is the normal extension of F. Any doubt up to here?
No, sir.
Okay. Now we have to prove that if part. Okay, second part. Wait a minute. Only if part now. Any doubt up to here?
No, sir.
No, sir.
Okay. Now suppose T is normal extension of F. Okay. And to prove that sigma of T contained in T for all sigma belongs to GKF. Okay. So all sigma belongs to GKF. Okay. Now that is to prove that sigma of T belongs to capital T. Okay. For all T belongs to capital T. Okay. Sigma of capital T contained in T. That means for any element of T, for all element of T belongs to T, we have to prove that this sigma of T कोणाचा एलिमेंट यायला पाहिजे टीचाच एलिमेंट यायला पाहिजे. ओके फॉर ऑल सिग्मा बिलॉंग्स टू जीकेएफ. Sigma belongs to GKF. Okay, any doubt?
No, sir.
Now, since T is the normal extension of F, since capital T is normal extension of F, this implies GTF is a finite group. GTF GTF. Okay, not now GKF. GTF is a finite group. It's a finite group, okay, of order say n. Okay, set of those automorphisms of T which leaves every element of F is fixed. Okay, set of those automorphisms of T which leaves every element of F is fixed. This is F. This one is T. Okay, but T is equal to what? We have F of A. Okay, now there are M elements are there. Okay, M automorphisms are there in GTF. Okay, what is the reason this for this statement? By corollary. What is that corollary? If K is normal extension of capital F, okay, this implies order of degree of K over F is equal to order of G K F. Okay, so this implies order of G K F is what? Finite. Okay, so this is the corollary. Okay, this is the reason for this one. Now, let there are m elements in GTF. That m elements are psi 1, psi 2, up to so on, psi m. These are the m elements. Okay, be all the m, all the elements, m elements of GTF. Okay, and assuming this 6 I1 be the identity, psi 1 be the, wait a minute, identity of GTF. Any doubt up to here?
No, sir.
Okay, now since GTF, what is the reason for this one? GTF forms a group, hence it contains it contains identity element. Okay, and let it be psi 1. Okay, now since A belongs to T, okay, which is equal to F of it. Okay, T is the simple extension of F. So taking A belongs to T, this implies psi 1 of A, psi 1 of A, psi 2 of A, up to so on, psi m of A. These are the elements of these are the elements of
T.
T. Why? Because psi 1, psi 2, psi m are automorphism of T. Na? So here if you apply this, all the automorphisms on the element of A, we get psi 1 of A, psi 2 of A, up to so on psi m of A are the elements of also T. Okay, right now. Because psi 1, psi 2, up to so on psi m are automorphisms, are automorphisms of T. Okay, that is T or psi is an automorphism. Okay, psi I is an automorphism from T to T. Okay, now again consider the polynomial. Which one? Consider the polynomial. If we observe the procedure to prove the theorem, okay, this is the same. Okay, by the in the previous theorem we also do the same procedure. Okay, let Q of x here. Q of x is equal to now x minus psi 1 of a, okay, into x minus psi 2 of a up to so on x minus psi m of a. Wait a minute. Okay, so this is the product of all the linear factors of x minus psi I of a, and we forms a one polynomial q of x. Okay, now this is the polynomial over
T.
t. Okay, give it as an equation number 2. So psi 1 of a, psi 2 of a, up to so on psi m of a. These are the polynomials. These are the elements belongs to capital T. So this q of x be the polynomial over t. Okay, again this implies q of x is equal to x raised to m minus beta 1 x raised to m minus 1 plus beta 2 x raised to m minus 2 minus up to so on minus 1 raised to m into beta m, where beta 1, beta 2, beta m are what? Beta 1, beta 2, up to so on beta m, okay, are
Elementary
highly
symmetric functions.
symmetric function. Elementary symmetric functions, okay, of the elements of elements psi 1 of a, psi 2 of a, up to so on psi m of a. Okay, is it clear up to here?
Yes, sir.
Of t. Okay, so now it can be easily seen that each beta I is invariant under psi, okay, in GTF. So it can be easily seen that it can be easily seen that each beta I, okay, is invariant with respect to psi in GTF. Okay, what is the meaning of this one? Psi I of beta I is equal to beta I. Okay. For example, look at here. What is B1? B1 is equal to summation I running from 1 to n. Okay, so this is sigma 1, sigma I of, sorry, wait a minute. This one is sigma I of A na. This is the value of B1. Okay, now if we apply the sigma and take sigma belongs to GTF. Okay, if we apply sigma on this one, sigma of beta 1, which is equal to, this one is sigma of summation sigma 1 of A plus sigma 2 of A plus up to so on, sorry, psi 1 of A, psi 2 of A plus psi m of A. हा इनव्हेरियंट कसा येते तो दाखवतोय मी. ओके, सो दिस इज इक्वल टू this one is psi of sigma 1 of A plus up to so on psi of sigma m of A. Okay, sigma belongs to GTF. All these psi I belongs to what? GTF. Okay, now the product of these two one belongs to GTF.
GTF.
GTF is a group. Okay, म्हणजे ह्याच्यात किती एलिमेंट्स होते एकूण? हाऊ मेनी एलिमेंट्स? m एलिमेंट्स. ओके, म्हणजे हा psi into sigma 1, sigma into psi 1 is equivalent to one of them, psi 1, psi 2, psi m. या कोणाला तरी एखाद्याला इक्विव्हॅलेंट येईल तो. ओके, psi sigma into psi 2 is equivalent to the product of these two automorphism is equivalent to one of them between psi 1, psi 2 up to so on psi m. Okay, so this is the what? Psi of beta 1. Again, Kai, this is summation. I running from 1 to m, sorry, the m. Psi I of a, which is equal to what? Beta 1. So here the beta 1 is invariant under sigma, where sigma belongs to GTF. Okay, similarly for beta 2, beta 3, we can show. Okay, any doubt now? हा कसा आला? कळालं? So beta I
Yes,
is
sir.
invariant with respect to psi in GTF. हे आपण प्रूव्ह केलंय का थेरम मध्ये मागच्या एका कुठल्या तरी थेरम? ओके, परवाच्या थेरम मध्ये प्रूव्ह केलंय पण. वेट अ मिनिट. Okay, so here the beta I is invariant with respect to psi in GTF. Okay, now since T is the normal extension of F, okay, what we assumed that since T is normal extension of capital F. Okay, so this implies fixed field of GTF is
F.
F. Wait a minute. So this implies fixed field of GTF is F. Okay. So what is F? F is equal to take the elements from K. Okay. This is F. T मधनं घ्या किंवा K मधनं घ्या किंवा T मधून घ्या. एकच असतं बेटा. Okay. This is F. This one is T. So this one is K. Okay. हा element इथून घेतला आपण. These are the elements from T and also K. So okay, the fixed field of F is equal to F. This means F is equal to take the elements from K such that sigma of A is equal to A for all sigma belongs to GTF. Okay, is it correct? The definition of fixed field of GTF. Okay. So that is equal to A belongs to capital K. On GTF मध्ये element कसे आहेत? Psi. Okay, so psi of A is equal to A for all psi belongs to GTF. Okay, any doubt?
No, sir.
Okay, now as BI belongs to F, all the BIs are invariant under psi, and BI be the element of what? These are the elements of F, na? B1,
Yes,
B2,
sir.
B1 are the elementary symmetric function of this one. Okay, so by the definition, हे invariant आहेत म्हणजे काय? If we apply psi on beta, we get beta I. So by the definition of fixed field, this all the beta i's belongs to F. So this implies by the definition of fixed field, beta I is element of capital F. Why? In the F, okay, in the set F, if we apply sigma on any element, we get A. So here we apply psi on beta I. What we get? This is beta I. So this beta I belongs to what? F. Okay. What is the reason for this one? Wait a minute. So this implies beta I belongs to F because psi of beta I is equal to beta I for all psi. Okay, so consequently, this q of x be the polynomial over now f of x. Okay, so from equation 2, wait a minute, from equation 2, we see that q of x has all the roots in T. Okay, all the roots in capital T. Okay, and also what is equation 2? Look at here. This one, x minus psi 1 of A, x minus psi 2 of A. What are the roots of this equation? Psi 1 of A, psi 2 of A, psi m of A. These all the roots of Q of X. Again, these are the elements of what? Psi 1, psi 2, psi m. These are the elements of T. So here the all the roots of Q of X are in T. And also psi 1 of A is equal to A is root of Q of X in T. Okay, and hence in K. If A belongs to T, so K is the superfield of T, and hence A also belongs to capital K. Okay, what is the reason? T is contained in K. Okay, now let now let sigma be any element of GKF. Okay, since sigma is an automorphism, sigma is an automorphism of capital K. Okay, leaving by the definition of GKF, leaving every element, okay, leaving every element of capital F fixed. Okay, and A is root of Q of X, which belongs to capital F of X in K. Okay, now sigma is a what? Automorphism on K, which leaving every element of capital F is fixed, and A is the root of Q of X, belongs to capital F of X in K. So we show that sigma of A is also root of Q of X in K, in capital K. Why? Because sigma is the automorphism from K to K. Okay, now let Q of X, what is Q of X? Is equal to x raised to m minus beta 1 x raised to m minus 1 plus up to so on. This one minus 1 raised to m into beta m. And what we have? A is root of Q of X in capital K. Okay, so this implies Q of A is equal to 0. So this implies A raised to m, apply put x is equal to here. So beta 1 A raised to m minus 1 plus beta 2 A raised to m minus 2 plus up to so on minus 1 raised to m. This is beta m. Okay, which is equal to what? 0. Why? Because Q of A is 0. Now apply sigma on both sides. We get sigma of this bracket, which is equal to sigma of 0. Okay, sigma is an automorphism. So what we get? Sigma of A bracket raised to m minus beta 1, sigma of beta 1 into sigma of A raised to, okay, that means sigma of A raised to m minus 1 plus sigma of beta 2 into sigma of A bracket raised to m minus 2 up to so on minus 1 raised to m into sigma of beta m, which is equal to sigma of 0 is what? 0. Okay, so identity maps to identity here. Okay, so from this equation, we can say that since sigma leaves every element of capital M is, sorry, say sigma leaves every element of capital F is fixed. We get this one. So this implies sigma of A bracket raised to M. Now beta 1 belongs to capital F. So this is beta 1. Sigma of beta 1 is what? Beta 1. Okay, into sigma of A into raised to M minus 1 plus up to so on. This is minus 1 raised to M into. This is sigma of beta M is equal to what? Beta M, which is equal
beta
to
m.
0. Okay, so this implies sigma A is a root of q of x. Okay, in capital K. Okay, since all the roots of q of x are in T, since all the roots of q of x, okay, are in capital T. This is the equation number third. Okay, so this implies now sigma A is what? Root of q of x in K. Okay, so this implies sigma of A must be must be element of T. Okay, पहा नीट पहा काय तुमचा F. This is F. This one is T and this one is K. Okay, sigma of A कुठं आला आता K मध्ये आला. But we have all the roots of Q of X are in T. Why? Because Q of X is the splitting field on T is the splitting field of Q of X. Look at here. Q of X is equal to all the roots of this Q of X polynomial over T. Okay. What are the roots of this one? This polynomial, psi 1 of A, psi 2 of A, all the these are the roots of Q of X are in T. Okay, so hence, तो K मध्ये नसून कशात असेल? Sigma A is the root of Q of X in K, but since all the roots of Q of X are in T, so sigma A must be in T. Okay? Okay. So here sigma A must be the element of T. So this is the equation number third. Okay, this one. Now T is equal to what? F of A is a finite extension of F. Okay, finite extension of capital F. Being a normal extension. We have T is the normal extension of F. Okay, being a normal extension. Now this implies what it implies? A is algebraic. A is algebraic of F. Okay, if A is algebraic of degree R, okay, suppose this if this A is algebraic of degree R, we have what we have. This implies the degree of F of A over F, which is equal to what is F of A? Degree of T over F is equal to R. Okay, so then if taking T belongs to capital T, any element of T belongs to capital T, be written as, okay, this T belongs to capital T, which is equal to what? F of A, na? So this T can be linear combination of again lambda naught plus lambda 1A plus lambda 2A square up to so on lambda r minus 1 into A raised to r minus 1. Okay, what is the reason for this statement? If A is algebraic of degree r, okay, then the nature of F of A is equal to lambda naught plus lambda 1A plus up to so on lambda r minus 1 A raised to r minus 1, where all the lambda I belongs to capital F. Okay, is it clear?
Yes, sir.
Now apply the sigma on both sides. So this sigma of t is equal to sigma of lambda naught plus lambda 1 a plus up to so on lambda r minus 1 into a raised to r minus 1. Okay. Now this implies sigma of t is equal to sigma of lambda naught plus sigma of lambda 1 into sigma of a. Okay, plus up to so on sigma of lambda r minus 1 into sigma of a raised to r minus 1, which is equal to lambda 1, lambda naught, lambda 1, all the elements of f now. Okay, so this is invariant under sigma. Okay, by the definition of sigma, this is sigma of lambda naught is lambda naught. Okay, sigma leaves every element of f is fixed, and here the lambda naught belongs to capital F. So here sigma of lambda naught is equal to lambda naught. This is lambda 1. This is sigma of a. Okay, plus up to so on. This is lambda r minus 1 into in the bracket sigma of a bracket raised to r minus 1. Wait a minute. R minus 1. Okay, so hence, what is the reason for this one? Lambda I are elements of capital F. This implies lambda sigma of lambda I is equal to lambda I. Since sigma leaves every element of capital F fixed, this implies sigma of t is an element as an element, give it as an equation number 4. Okay, sigma t is an element of capital T. Okay, what is the reason for this one? Since sigma of a belongs to capital T and lambda naught, lambda 1 up to so on lambda r minus 1, these are the elements of f which is contained in T. Okay, so from equation 4, what is the equation 4? Here, the lambda naught belongs to T, lambda 1 belongs to T, sigma of A belongs to T, lambda r minus 1 belongs to T, sigma of A bracket raised to r minus 1, this also belongs to T. So hence, this sigma of small t, this element belongs to T. Okay, so from equation 4, we have this sigma of T, okay, is written as linear combination of elements of capital T again. Okay, thus for every sigma belongs to G, K, F and small t belongs to capital T, what we have? Sigma of T belongs to capital T. That implies for every T belongs to T means what? If we apply on whole the field T, this sigma of T contained in T for all sigma belongs to G, K, F. Okay, hence the proof. Any doubt?
Go, go, go. Okay, go. Oh, what the heck? Machine मध्ये सोडती
Okay.
मग तू केली नाही तर. अव्वा मशीन अव्वा आली 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 तर तिला घाबरते.
Any doubt up to here?
No, sir.
थोडं स्पीड झालं पण वाचा नीट, वाचल्यानंतर व्यवस्थित समजेल. ओके, हा इक्वेशन 3 आणण्यासाठी कारण काय? हा सिग्मा ऑफ ए मस्ट बी इन टी. ओके, सिग्मा एफ. ओके, एनी डाऊट अप टू हियर? एक 2-3दा वाचा म्हणजे व्यवस्थित समजेल. प्रोसिजर सगळी सेम आहे. ओके, कालचे 2 थेरम, कालचा एक थेरम आणि त्याचा परवाचा एक थेरम, प्रोसिजर सगळी सेम आहे. एक 2दा वाचा व्यवस्थित म्हणजे समजून जाईल. Okay, wait a minute.